Okay, section 5.6 is on properties of linear relations. And we've already talked about relations being an association between two quantities. So a linear relation is a special type of a relation that has a graph that looks like a straight line. And to determine if a relation is a linear relation from a table of values, you basically look at the x and y values in your table. If the x's are increasing or decreasing by the same amount, then you can look at the y's, and if they are increasing or decreasing by equal amounts as well, then you can determine that it's a linear relation. If the x's aren't increasing or decreasing by equal amounts, you can't really look at the y's to see if there is going to be a relationship there. It's not going to help you determine if it's a linear relation. So you'd have to either look at another way of determining if it's a linear relation, probably graphing or something like that, because you can't really tell if the x's aren't going up by the same amount. You can't use this method. All right. So in this case here, it is a linear relation because you can see that the x's are going up by 5s and the y's are all going up by 3s as we increase from one point to the next. So when we're looking at a linear relation, we can figure out the rate of change, which is your change in your dependent variable over the change in the independent variable. And by the way we've looked at the last table here, we can easily see that the change in the dependent variable is always 3 between consecutive points, and the change in the independent variable is always 5. So if we look down at the little bubble there, it kind of gives you a little hint that a lot of times when you're looking at a rate of change for a linear relation, if you include the units with your dependent variable and your independent variable, it can kind of give you a hint as to what the rate of change represents. So for example, if your dependent variable was representing kilometers and your independent variable was representing hours, then you would have a rate of change representing kilometers over hours. So that would be kilometers per hour, or speed in this case. Okay? If your dependent variables represented cost and your independent variables represented the number of copies of something, then you would have cost per copy would be your rate of change. Okay, so try to include the units. The one we had just finished now didn't have units, so it's just a rate of change. But a lot of times, like I said, you can figure out what the rate of change is representing based on looking at the units that the dependent and independent variable represent. So below we have some examples of linear and non-linear relationships. So if you look at the first one there, it is a linear relation, and you can check from the table by noting that every single x, as you go from one x to the other, you're increasing by 1. From 1 to 2 is an increase of 1, 2 to 3 is an increase of 1, from 3 to 4 is an increase of 1, and from 4 to 5 is an increase of 1. So if we look at the y's in the table, they're all going up by 4s. So from 8 to 12 is 4, 12 to 16 is 4, 16 to 20 is 4, you're adding 4, and 20 to 24, you're adding 4. So the equation that was used to generate that table was y equals 4x plus 4, and the rate of change, if you look at the change in the dependent variable, was 4, over the change in the independent variable was 1, and that equals a rate of change of 4. We don't know the units for y or for x, so we can't include the units there. If you look at the next example, the nonlinear relation here, the x's are going up by 1s all the way down. But if you look at the y's, the first one goes up by 6. From 2 to 8 is a change of 6, add 6. But then from 8 to 18 is a change of 10. So right away we can stop now, because we know that even though the x's are going up by 1s, the y's aren't going up by the same amount each time. So it's not a linear relation. And if you look at the equation that was used to generate that table, it's y equals 2x squared. And it's significant that the x squared is in there, because when you have an x squared, as you'll learn as we move through the chapter, and this chapter and the next chapter, that does not have the form of a linear equation. So if you look at the next example, it is a graph of a linear relation. It has points that if you were to connect them would be connected in a straight line. So you can see visually that it is a linear relation. And if we check the x and y values of those points, you can also check, similar to what we did in a table, that the x of the first point is an x-coordinate of 2. And the x-coordinate of the second point is an x-coordinate of 3, and then 4, and then 5, and then 6. So they would be, the x's are increasing by 1s. And then if you look at the y's, it starts off at a height of 4 for the first one, then down to 2, then down to 0, then down to -2, then down to -4. So the y's are going down by 2. So it is showing a pattern of increase in the x by the same amount and decrease in the y by the same amount. So therefore it is a linear relation if we check it that way as well. So if we check the rate of change, we just checked there that the y's were going down by 2, so that would be a -2, and the x's were going up by 1s, so that would be a rate of change of -2 over 1 or -2. And the last one obviously is not a linear relation, because when you connect those points, they're not in the pattern of a straight line. There's a curve involved. So that would be obviously not be a linear relation. So linear relations can be identified in several ways. We looked just a few moments ago at the table of values, and when we considered the graphs, looked at some of the ordered pairs and how they relate. If they show a constant rate of change for the variables, meaning the x's and go up or down by the same amount, and the y's go up or down by equal amounts as well, then it would be a linear relation. We also saw from the last couple of examples that the graphs which have a line, pattern in the shape of a line, would be considered linear graphs. And also another way to look at it is by looking at the equation. And the equation has the form of dependent variable equals your rate of change times independent variable plus the initial amount. So if an equation has that kind of a form, it is generally a linear relation. So when we look at the first example here of an equation, we have C, which probably represents cost, equals 0.06 times t, which probably represents time, plus 50. So cost would be our dependent variable. It is equal to 0.06 times our independent variable. So in this case, 0.06 would be filling in the rate of change spot. So that would be our rate of change of cost over whatever units of time. And then we have the independent variable would be t, and then the initial amount would be 50. And what we mean by the initial amount is when your independent variable is 0, the value of your dependent variable. So in this case here, if time is 0, the cost would equal 0.06 times 0 plus 50. So the cost would be 50. So that would be your initial cost, or the cost before any whatever time, units of time, if it's hours or minutes, accumulate. Okay? So if we look at an example here now of a relation described in words, the relation describes the cost for the rental of a banquet hall as $150 plus $25 per hour. And we're assuming that partial hours are rounded to full hours for calculating rental costs. So if we look at the table of values and do a sample table of values for this particular relation, for 0 hours, it would be $150. For 1 hour, it would be your $150 plus your $25, so that would be $175. For 2 hours, it would be your $150 plus 2 times 25, or 50, so that would be $200, and so on. So if you look at our table of values, you can see that as the hours go up by 1 every time in our table, the costs are going up by 25. Okay, so our rate of change would be, the change in the dependent variable is 25. over the change in the independent variable is 1. So the rate of change, would be $25 per hour. And if we look at the graph of this relationship, we would have your cost would be your dependent variable, so that would be on your vertical axis, and your hours would be the independent variable, and that would be on your horizontal axis. So we had 0 going with 150, we had 1 going with 175, we have 2 going with 200, we have 3 going with 225, and 4 going with 250. And you can see by using the graphing method that it is a linear pattern as well. And we wouldn't connect the points here because we just said at the beginning there that partial hours are rounded to full hours, so we wouldn't be able to calculate a charge for partial hours. If we look at the equation using the little description above, our equation, because it represents a linear relation, so as we can see from the table and from the graph, that it is a linear relation, it should have the form that the dependent variable is equal to the rate of change times the independent variable plus the initial charge. So in this case, if we use C for our dependent variable, as it is on our table in our graph, the dependent variable C, it's equal to the rate of change, 25, times the independent variable, which is the number of hours, plus the initial cost would be at hour 0, which would be 150. And if we check that equation and plug in some values for hours like our table, you will see that it will generate exactly the table that we have given there at the beginning. If we plug 0 into there, 25 times 0 plus 150, that will give you 150. If you plug in 1 for the hours, you get 25 times 1 plus 150. So that gives you 175. If you plug 2 in there, you will get 200 and so on. So the equation is correct. And you notice that the rate is right in front of the variable, the independent variable. The same rate that we found in our table over here. All right, so the next examples ask you to determine whether or not the relation that's given represents a linear function and identify the rate of change for the linear functions, including units if possible. Notice we're using the word function now because if it is a linear relation will also be a function. All right, so for the first one here, these C's are all going up by 5s in the table. Check each one of them. Each time it goes up by 5. And the Y's, or the Fahrenheits in this case, the second elements, the dependent variables, are going up by 9 each time. So it is a linear relation. And because this is linear, we're asked to identify the rate of change. So the rate of change for this one would be the Y's or dependent variable is changing by 9, and the independent variable is changing by 5. And that would be degrees Celsius or degrees Fahrenheit. And you might want to change that to decimal of 1.8 degrees Celsius for every degree Fahrenheit. Okay, so the next example, if you check, the times are going up by 10. If you check each one of them, they're going up by 10. And that's going up by 10. And that's going up by 10. But if you look at the volumes, the dependent values, that's going down by 7. And then that's only going down, that's going down by 8. So right away, this is non-linear. So we don't have to find a rate of change for that one. And then we look at the next examples, our lists of ordered pairs. The first one, the x's are going up by 1. Up by 1. Up by 1. Up by 1. But the y's are going down by 6 for the first one. But then 5 to 3, that's only going down by 2. So this would be nonlinear. So again, we don't have to find the rate of change for the nonlinear ones. The next one, we look at the x's, they are going up by 3. First one, -7 to -4, add 3 is going to give you -1, add another 3 is going to give you 2, add another 3 is going to give you 5. So that is, the x's are going up by a constant amount of 3, and the y's are going, first set of y's, 10 to 8, that goes down by 2, 8 to 6 goes down by 2, 6 to 4 goes down by 2, and 4 to 2 goes down by 2. So this would be linear. And the rate of change would be change in the dependent or y values over the change in the independent or x values. So that would be -2 over 3. Our next example is a graph, and we have, obviously, looking at it is a straight line pattern, so it would be a linear pattern. So the rate of change for this one, again, you can look at take any two nice points on the graph. So I'm going to pick this one here and this one here. And if you look at the rate of change or change in the y coordinates over the change in the x coordinates, you have here from this point to this point, the change in the y coordinates is 250 minus 150. And then if you look at the change in the x's from the same 2 points, this first point, we had an x of that would be 5 minus the x of 10. So that would give us 100 over -5. And that makes sense because this is decreasing. The kilometers are decreasing as the hours go on, so it should be a rate of change of -20 kilometers per hour. And what do you think the negative means? Because usually when you see kilometers per hour, you think of speed, so you wouldn't normally have a negative. So what that's indicating to you here is that in this case, it's probably the distance is decreasing. This negative indicates that the distance is decreasing. As time goes on. And the next and last graph here on this page is obviously not a linear relation. It doesn't have that straight line pattern. The next example is an equation. So when we look at the equation, it does have that form of dependent variable is equal to the rate of change times the independent variable plus a constant, or in this case minus, plus or minus. So the initial amount, in other words. So this one would be a linear relation. So therefore linear relation. And the rate, if you remember our form of the equation, the rate would just be 0.35. And we don't know the units of what P and T represent, so we'll just leave it at 0.35. The next equation has F equals 0.35 h squared plus 5h plus 25. So when we see the h squared there, we know that this is not a linear relation. It does not have that form like G had of dependent variable equals rate times independent variable. There's a h squared term there. So this would be nonlinear. Okay, the next example shows different kind of situations, and you kind of have to decide whether it's a linear relation or a nonlinear relation based on the description. And as you go through different types of equations in this year and next year, when you look at these statements, you'll probably be able to tell just by reading the statements whether it's linear or nonlinear. But now that we're only just learning linear, probably the easiest way to tell you to decide in this case is to do up a table of values where you deliberately pick x's that are going up by the same amount and see if the dependent values that are associated with those independent values go up by or go down by equal amounts as well. So in this case here, we would have an investment of $500 increases in value by 10% each year. So if we have our independent and dependent variables assigned, we would know that the value of the investment depends on the time. So the time would be our independent, time would be the year, and the value in dollars would be our dependent variable. So if we pick time 0, that would go with a $500 value, and after 1 year, that would be going up by 10%. So 10% of 500 would be $50, I'm sorry. So 500 plus 50 would be your value of the account after 1 year. So then if you go up another year, so 2, you would have 550 times 10% added on to 550, or a quick way to do that would be 550 times 1.10%, because that stands for 110%. So you'll be taking 100% of the value you had plus an extra 10%, and that gives you 605. So right away there we can see that they're going up by 50, and now it's going up by 55, even though the x's were going up by 1s. So this would be nonlinear. And the next one, if we look at this particular description, it says a service technician charges $75 flat rate plus $30 for each hour he works. So this one here would have, you can do it a couple of ways. You can do it thinking in terms of an equation. The charge would equal $30 an hour plus a $75 flat rate. So that has a linear pattern. Now, if you're not convinced with that, you can do a table of values, and you could just take a couple of hours. Oops. A couple of times, like, so the first, this one here, the charge, would depend on the hour, how many hours worked. So 0 hours would just be $75. 1 hour would be 75 plus 30, or 105. 2 hours would be 2 30s, which is 60. 60 plus 75 is going to be 135. And if you check, these are going up by 1s. And as every hour increases, these are going up by 30. So it is a linear relation. So either way, you can use the equation, or you can use a table of values to kind of show that it is a linear relation. Okay, the next example says a culture of bacteria initially contains 60 spores but doubles in size every 3 hours. So in this case here, our dependent variable would be the number of spores, and our independent variable would be time. So we do a quick little table, so time in hours, and the number of spores. So time in hours, so for example at time 0 it would be 60, but then after 3 hours it doubles in size, so that'd be 120. So after another 3 hours, which would be 6 hours, it doubles in size again, so that would be 240 spores. So if we look at the x's, or the times, they are going up by the same amount, going up by 3 every time. But if you look at the dependent variable values, they're going up by 60 the first time, but then 120 the second time. So this would be nonlinear. And the last example on this page says a taxi charges a flat rate of $4.25 plus 75 cents per kilometre. So again, that kind of has that form of the equation that we were talking about earlier. The dependent variable is the rate times the independent variable plus the initial value. So in this case, our dependent variable will be the charge, and our independent variable will be the number of kilometres. So we could actually come up with an equation. This is the charge would equal 75 cents a kilometre. So if we say K for the number of kilometres, plus $4.25. Don't actually need to have those dollar signs in there, but okay, so that would be a linear relationship. It has that form. And again, you can do a table of values like we did for B if you weren't convinced that that was the right equation, and you would see that it would be a linear relationship. Okay, next example, it talks about Marble Mountain Ski Resort, and it has a peak elevation of 550 meters. Robert has never skied before, and after traveling up the mountain on ski lift, he changed his mind about skiing down the mountain due to his fear of snow. So as a result, he refused to get off the chairlift and returned to the base of the mountain, which has an elevation of 100 meters. So graph A represents traveling up the mountain on a ski lift, and graph B represents traveling down the mountain on a ski lift. So if we look at the questions below and answer them according to these graphs, the first question is asking you to identify the independent and dependent variables. And in both cases here, the independent variable would be time. And typically the independent variable is on the horizontal axis, so time in minutes for both of these graphs. And the dependent variable for both graphs is the altitude, or height. And that's in meters. The next question asks you to determine the rate of change for each graph. So when we're looking for the rate of change, we're looking for the change in the dependent variable over the change in the independent variable. And an easy way to do that is just to pick two nice points on the graph. So I'm going to pick the first one in the first graph here. I'm going to pick the first initial point, 0, 100. And I'm going to put the last point here, 20 and 550. So if we kind of draw a little path from one point to the other, we can calculate the rise between those 2 points, or the change in the dependent variable, which would be from 100, height of 100, up to a height of 500, so that would be 400 meters. And then we can look at the change in the independent variable, which would be from 20 back to 0, so that would be 20 minutes. So for graph A, our rate of change would equal, the change in the dependent variable is 400 meters over 20 minutes or 20 meters per minute. In the second graph, if we do the same kind of thing, we can pick the first point and the last point as well, or we can pick any two nice points on the graph. And what I mean by nice points are nice points where the point is right on the grid line, so that you can easily read the x-coordinate and easily read the y-coordinate. So I'm just going to pick these 2 points down here because these are both nice points. They both have easy x-coordinates and easy y-coordinates to read. So we kind of draw a little path from one point to the other. We're going, can't seem to get that right on the right spot there, it's close enough. So we're basically going up from 100 up to 200, so that's up 100. So the difference in the, the change in the dependent variable will be 100 meters, and then we're going to the left from an x-coordinate of 18 minutes to an x-coordinate of 14 minutes, which would be 4 minutes. So that would be a rate of change of 100 meters over 4 minutes. But if you look at this particular graph here, it's the altitude is going down as we move forward in time. So as we move to the right, it's going down. So this would be a negative rate of change. So that would be negative 25 meters per minute. So just going back to kind of go over that idea there. So basically, if you look at in terms of directions from one point to the other, we went from this point, we went up 100, that's a positive direction up, and left 4 minutes. So that would be a negative direction. So 100 to -4, you can do it that way, like rise over run kind of thing, or you can just count how high you've gone up for the change in the dependent values, and then count how much of a change there was in the independent values, and then look at the shape of the line. If it's falling as you move to the right, then it would be a negative rate of change. If it's like the first graph, as you move to the right, the graph is rising, that would be a positive rate of change. So if we go back for a minute here, you can see that in terms of answering the question, which rate is faster, ignoring the fact that one is increasing the altitude and the other one is decreasing the altitude, so ignoring the negative, we're actually, he's actually coming down the mountain at a faster rate. So the rate that's faster would be graph B. Graph B's rate. He's descending at a rate, because the negative would mean going down. Altitude is decreasing. Graph's B rate. Okay, he's descending, descending at a rate of 25 meters per minute. Okay, our next topic is on graphing functions. So when graphing functions such as y equals 3x plus 1, which have that linear equation pattern, it can be quite helpful to create a table of values in order to find the points that correspond with this equation. And then you can take those points and plot them on the graph. And we know that linear functions should have a graph that looks like a line. So if we take some possible x's for this particular equation, we can choose -2, -1, 0, 1, and 2. And if we plug in -2 into the equation, we would have, just do our workings off to the side here for the first couple, so it'd be 3 times a -2 plus 1, which would be -6 plus 1, so that would be -5. And then we take the second one there, y equals 3 times a -1 plus 1, so that would be -3 plus 1, which would be -2. And 0 will be 3 times 0, which is 0 plus 1, which is 1. And y equals 3 times 1. If x is 1, that'd be 3 times 1 is 3, plus 1 is 4. And if we put in 2 there, 3 times 2 is 6, plus 1 is 7. So the graph already has the x and y axis labeled for us. We can just plot those points now. So -2 goes with -5. So that would be about right to here. And -1 goes with -2. So that would be about right here. 0 goes with 1. 1 goes with 4. And 2 goes with 7. And we can connect those because we're not told that x or y represent anything particular, so we can just assume that all the numbers in between are possible as well. I can't draw a very straight line with this stylus. Apologize for the shakiness of my line. Okay, so you can see that it has a linear pattern. So if we look at these next examples to see which ones are linear, and we just do the same type of thing. Some x's are picked there for us, and we just figure out the y's that go with them. So for the first example, we have to square the x, so -2 squared is going to be 4, times your 2 is going to be 8. 8 minus 1 is going to be 7. We're just plugging it into this equation right here. We're putting the x value in and following the order of operations. So squaring has to be done before you multiply by the 2, and then you subtract the 1 after. So then -1 would be -1 squared, which is 1, times 2 is 2. 2 minus 1 is 1. 0 would be 2 times 0. Well, 0 squared first, so 0 squared is 0. 2 times 0 is 0 minus 1. 1 would be squared and still give you 1. So then multiply by 2 is 2. 2 minus 1 is positive 1. And then we'd have 2 squared would be 4, times 2 is 8. 8 minus 1 is 7. So if we plot these, we've got -2 and 7. We've got -1 and 1. We've got 0 and -1. 1 and 1. And 2 and 7. So this graph is definitely not a linear graph. Not linear. It's actually the graph of a quadratic equation, which we'll do later on this year. Introduce it a little bit, and then next year you'll do a little bit more with it. So then the next equation, we plug in the -2. We've got -3 times -2 is 6. 6 plus 2 is 8. -1 would be -3 times -1, which is 3. 3 plus 2 is 5. So again, we're plugging into this equation now. And -3 times 0 is 0, plus 2 is 2. -3 times 1 is -3, plus 2 is -1. And -3 times 2 is -6, plus 2 is -4. So if we plot those points, -2 goes with positive 8. -1 goes with 5. 0 goes with 2. 1 goes with -1. 2 goes with -4. We kind of suspected that this is going to be a line because the equation I think I'm drawing a straight line, but it doesn't come out looking like a straight line. Okay, It has that pattern that we talked about earlier about the dependent variable is the rate of change times the independent variable plus constant, has that form. The next equation, so this one, sorry, go back, this one is linear. Has that linear straight line pattern, though my line doesn't look very straight. Okay, the next one is y equals 4, so that's kind of a strange looking equation, but basically what that means, no matter what x we put in there, -1, 0, 1, or 2, or 3, the y will constantly be 4. No matter what x we pick, the y will be 4. So that is basically going to be a line that goes through all these points at a height of 4, so that would be a linear straight line. And that's actually a horizontal line. So the next one, the x is constantly -4. So you can't pick anything else but -4 for x. So that means it doesn't matter what y is. Your x is -4, so -4 will go with -1. -4 will go with 0, -4 with 1, -4 with 2, -4 with 3, and so on. So it's basically a straight line that goes through the same x coordinate of -4. So this would be a vertical line, what we call a vertical line. And this would be linear as well. Has that straight line. So if we look at those last two there, anything that has, basically you can probably realize that anything that has the form y equals a constant would be a horizontal line, and any equation that has the form x equals a constant would be a vertical line. So there's some questions down there now at the bottom on pages 308 to 310 that you can try to practice some of the concepts we've learned in this section.